when you get in a car, you feel it sink down as the springs in the suspension compress. When you get in a lift, you might notice that drop down a little bit as the metal cables holding it up stretch a little bit. When you walk onto a bridge, you might not feel it, but the whole bridge will go down just a little bit. In fact, the whole world around us is always changing shape. And what we're going to learn about in this lesson video is how we can start to design for that. It's all about forces, of course. A force can do three things to a body. It can change the body's speed. It can change the body's direction. And it can change the body's shape. Now, for this last one, I like to think of it as the speed of the front surface of the ball changing, but the speed of the back surface hasn't changed yet, so the ball changed shape. Anyway, it's all down to forces. To analyse what is going on, we turn to a classic and extremely important experiment, measuring the extension of a spring to find its spring constant, K. The higher the value of K, the stiffer the spring. Now, you might have done this before, but let's look at it anyway because it is so fundamental to so many parts of physics and engineering. Let's do it right. Alright, so the key equipment is a spring which is suspended from a clamp. Make sure the clamp is not wobbly. We need a ruler to measure the length and extension. And this is where care comes in. Most students just hold up a ruler and get on with things, but it only takes a moment to set things up properly and avoid risking getting rubbish results. So when you go to get the stand and clamp, get yourself a second clamp. You can get a second stand if you want, so you can clamp the rule in position. Obviously, make sure you use a calibrated meter rule, not your freebie ruler that could easily give you incorrect results. I once saw a student using a 30 centimeter ruler that was only 28 centimeters long when I checked it. So get into the habit of grabbing the extra clamp, and you've put in 0 effort so far. Now clamp the rule in position next to the spring, leaving enough space for the mass hanger to hang without touching the rule. For bonus points, use a set square on the bench to ensure the meter rule is vertical. We are going to assume the bench is horizontal, by the way. Now, fix a pointer to the spring or the mass hanger. This needs to be rigid but light. A toothpick, for example. This is going to point at the meter rule, and that's going to eliminate parallax error. At this point, you'll have spent a couple of minutes longer than other students, but you're in a position now to race through the rest of the experiment and get stellar results along the way. So, record the current reading of the pointer. This is your original length. It might be the actual original length, that's nice, but it's not important. Add a mass, gently. Don't overextend the spring, and record the new reading. Add another, etc., etc. Now, since the rule doesn't move, you'll be able to do this super fast. Just don't overextend the spring at any point. Now you have a table of load and length. You can fill in another column for extension, which is length minus original length. Then plot a graph. If we put F on the y-axis and extension on the x-axis, and we get a straight line through the origin, because we're so good at experimental work. Then, from maths, we can see that the equation for that graph is y equals mx, or in this case, f equals gradient times x, which looks like f equals kx, where k is the gradient, a constant, and we call that constant the spring constant. So that's Hooke's law and how to do experiments like a pro. Take time to set up properly at the start, and not only are you going to get excellent results, but you might well save time overall. We've also looked at Hooke's law using the equation f equals kx and how to get the spring constant k from the gradient of the graph. At the moment, we're just looking at that nice linear region. We'll look at it when we overextend the spring in another video.